Hello and welcome back to Unit 5. In this part of Unit 5, we're going to look at two examples where we use the model for friction developed in the last part. In the first example, we have a car skidding to a stop. It's a 1,200 kilogram car. It slams on its brakes, locks up its wheels, comes to a stop. We want to know what is the force of friction between the car and the road, and what is the car's acceleration. If we look at the table provided at the end of the last part, for rubber on dry concrete, we have a static friction coefficient of 1 and a kinetic coefficient of friction of 0.7. And for rubber on wet concrete, it is a range of 0.5 to 0.7 for static friction, and the kinetic friction is between 0.3 and 0.5. Now we have to decide what type of friction are we dealing with here. Well, the car has its wheels locked, which means they're no longer rotating. Because they're no longer rotating, this car is essentially a block sliding across a road, and that means that we're going to be dealing with kinetic friction. Drawing a picture of what is going on. Here is my car. It is moving this direction, but because it's coming to a stop, the acceleration is in the other direction. Okay. I'm going to use a standard XY coordinate system where X is to the right and Y is upward. I can now draw the free body diagram of my car. I have a normal from the road on the car. I have the car's weight pulling downward. And I only have one force horizontal, and that is the friction between the road and the car. Okay. Remember, again, the car's wheels are locked up. They cannot rotate. The only force I have horizontal on the car is friction in this case. Looking at the vertical direction, the Y direction, we have no acceleration in that direction, therefore the net force in the vertical direction equals 0. I'm going to take all forces upward, subtract off all forces downward. This gives me that the normal force on the car equals the car's weight, which is the mass times gravity. Given a 1,200 kilogram mass and 9.8 meters per second squared for gravity on Earth, this tells me that the normal force between the car and the road is 11,760 newtons. If I go and look horizontally, in the X direction, I only have one force. That is the force of friction between the car and the road. Given the coordinate system I established, that is a negative force. But also given the coordinate system I established, my acceleration is in the negative direction as well. So now I can find that the acceleration will be the force of friction divided by the mass in magnitude, and we know already it is going to point to the left in our coordinate system. To find the force of friction, I use the model that was developed in the last part of the problem, where it's going to equal the kinetic friction multiplied by the normal force. For part A, remember the kinetic friction equaled 0.7. So FRC will equal 0.7 times 11760 newtons as found using the vertical direction. And that gives us a force of friction of 8,232 newtons. For part B, kinetic friction was bounded somewhere between 0.3 and 0.5. Therefore, the force of friction is somewhere between 3,528 newtons to 5,880 newtons, where these two numbers were found by taking 0.3 times 1,000 or 11,760 or 0.5 times 11,760 newtons. I can now take these two values for these values for the force of friction and answer what is the acceleration. So for part A, the acceleration will be 8,232 newtons divided by the mass, which is 1,200 kilograms. And that equals 6.86 meters per second squared. For part B, again, it is bounded, but using my upper and lower range for the friction, I get the acceleration is somewhere between 2.94 meters per second squared to 4.9 meters per second squared. Not a huge surprise that the acceleration of the car is much smaller when the pavement is wet. Moving on to the next question. The next question deals with rearranging a room. In this case, we have a wooden cabinet sitting on a wooden floor, and you want to relocate it. Okay. Using again the table provided at the end of the last part, wood on wood has static friction of 0.5 and kinetic friction of 0.3. Okay. The first question asks, how much force is it needed to get it moving? So this is basically asking, how hard do you have to push if static friction is maximized? Okay. How much force is needed to keep it moving at a constant speed? So now we're looking at how much force do we have to apply given kinetic friction. And the last part asks, assuming it is moving at 0.3 meters per second, how quickly does it come to a stop if you stop pushing it? This is again dealing with kinetic friction, but in this case, we're accelerating. So as always, I like to begin these problems by drawing a picture. So here's my big old wooden cabinet, and here's me trying to push it. I'm going to use a standard XY coordinate system. It doesn't say it in the problem, so I am going to assume that I am pushing horizontally on the cabinet. That simplifies the problem because now all forces lie either along the x-axis or along the y-axis. If I look at the free body diagram, there are four forces. There's the normal force between the floor and the cabinet pushing upward. There's the force from my push pushing to the right. Gravity is pulling downward, and friction is going to the left because it is opposing the motion. I'm going to begin by looking at forces in the vertical direction. There is no acceleration in the vertical direction. There is not going to be an acceleration in the vertical direction. Therefore, the net force equals 0. My two forces in the vertical direction are the normal force pointing up, the gravitational force pointing down, so I subtracted it off. That tells me that my normal force equals the weight, which is mg, which is 45 kilograms times 9.8 meters per second squared, which works out to be a 441 Newton force. I'm now going to switch over and think about the x direction for each part of the problem. For the first part, to get it moving again, this is max static friction. Okay. Maximum static friction occurs when the static friction equals the coefficient times the normal force. In this case, the coefficient was 0.5, and the normal force we just found to be 441 newtons, and that equals 220.5 newtons. Since it is not moving, the net force in the x direction is 0. I have two forces in that direction. I have my push minus the friction. I used floor, right? I'm trying, oop. Yes, I used floor. Okay, I'm making sure my subscripts agree. That equals 0, and that tells me that the amount I am pushing equals the maximum value of static friction, which equals 220.5 newtons. For part 2, where kinetic friction and constant speed, which tells me again that the cabinet is not accelerating. In this case, friction will be kinetic, which will be the kinetic friction coefficient times the normal. Kinetic friction coefficient was 0.3 times 441 newtons, and that works out to be 132.3 newtons. Now applying Newton's second law. Again, that the normal equals the force of friction, and therefore equals 132.3 newtons. For part 3, it's accelerating. Okay. And I'm no longer pushing. So the normal from, that's a me on the cabinet, equals 0 newtons. I'm not pushing any longer. Hands off, if you will. If I think about the x direction, given that that normal force is 0, I have that the kinetic friction between the floor and the cabinet has to equal the mass times the acceleration. So the acceleration will equal the force of friction divided by the mass, which works out to be 132.3 newtons divided by 45 kilograms, and is 2.94 meters per second squared. The 132.3 newtons is what we found, you might remember, in the last part for the force of friction. It is still valid here because it is kinetic friction still, and kinetic friction is single valued. This question is not asking what the acceleration is. It wants to know how quickly does the cabinet come to a stop. Knowing the acceleration and how quickly it is moving to begin with, we can use our constant acceleration equations. Again, we're making an assumption that the acceleration will be constant, to find that time. So at t equals 0, I'm going to let it be at x equals 0. But it is moving at 0.3 meters per second as given in the problem. It looked like 10.3. I'm fixing it. Okay. At an unknown time later, it's traveled some distance, but it has come to a stop. I'm going to let positive be to the right. My initial velocity is to the right. My acceleration is to the left. Time is what I want to know. In my coordinate system, my acceleration is a negative 2.94 meters per second squared. My initial velocity is 0.3 meters per second. My final velocity is 0. Initial position is 0, and I don't know where it ended up, how far it traveled. The easiest way to find time in this case is to use the V equals V naught plus AT formula. So time is going to be the difference in our velocities divided by the acceleration, which is 0 meters per second minus 0.3 meters per second divided by 2.94 meters per second squared with a negative there. And that gives that the cabinet will come to a stop in just over 1/10 of a second. This concludes this part of this unit. In the next part, we have 2 more examples we're going to look at.